Hello everyone, my name is Shakti and today I'll be presenting my team's work on site, that is Semantic ID Embedding for effective learning from sequences. So this is the agenda we'll be following. Let's head into motivation. User histories typically range in the order of 10 power 3 to 10 power 4, and these features are very large embeddings of D dimension where D can be very large, approximately 400 to 1000, and hence they incur significant storage and inference cost. And so we need to reduce these three dimensions of features by, in order to increase dimension X so that you can use longer sequences. We also need to, use more features and pack more information in order to improve the ads recommendation. And trying to compress all these three dimensions will reduce our feature capacity cost. So why side? We make three specific contributions. The first is we compress these large D-dimension embeddings into feature of length L, where L is very small compared to D. We are method discrete PCA. The second is we compress multi-inputs to generate a single output. So now you don't have to use n features as input. You just have to use one feature through our method VQ fusion. And third is we don't need embedding tables. So this is an embedding free lookup approach, and this through this we can express much larger embedding space because now there's no hash collision, and also save on model storage. So let's look at side encoders. Vector quantization has been used for mapping high dimensional features into discrete IDs that can help build a high quality representation of the high D feature. Residual quantization here develops hierarchical learning where you're now modeling residues at each layer and use these IDs C1, C2, C3 as your input features. And this form of a model is trained as an autoencoder, which leverages reconstruction loss and codebook loss in order to make sure that the codebook doesn't collapse. Relearning ID to coded embedding mapping requires large amount of data because these points are initially random in KNN. And so we develop an extension to this KNN type algorithm where all these points, we introduce structured collinearity between them. And additionally, we also introduce targeted encoder model heads so that this head can predict video embedding, this head can model image embeddings, this head can do ID prediction. So now a single encoder, fusion encoder model is able to do multimodality features. So now you can have multiple features as input, you'll just have one feature as the output. Our first contribution, DPCA, is an extension of finite scalar quantization. What we do is we choose the line closest to the given point, get the distance to this line, and get the projection and quantize this projection weight as k. Now, in terms of DPCA, we also realize that a vector codebook is redundant when you're using it in conjunction with residual quantization or product quantization. And so we set the number of vector code words as just one, and we only use three values, -1, 0, and 1 as the codebook sign distance or the quantized projection weight. And this follows from recent work in 1.58-bit LLM, which says that a ternary codebook could be universal for LLM weights. And thus with these two extensions, vector code word 1 and 3 values, we arrive at our algorithm discrete PCA. Now, this is the typical output that we see from discrete PCA. How do we transport it, convert this into a feature? So we convert it to a collection of n-gram SIDs, basically combine these values with a base power and sum it up to get this n-gram. And this n-gram can be reversibly 4 modulo and converted to a representative embedding back. So this is the ID that is transported to the ads ranking model as a feature. So typically you would get the SIDs, you would do an embedding lookup, learn the embeddings, and this would require ON cross T memory. But with our method side, because these can be deterministically unpacked back to the encoder outputs, we do this deterministic unpacking within the model, ads ranking model, and just linear project to get the appropriate shape of the model and use them as embeddings. So now there's no extra memory required. Let's look at how this is used in ads ranking. uh, in ads ranking, for ad side features, they usually have two dimensions. First is the batch size, second is the feature dimension. We take the features, quantize them using our side model, and in the ads ranking model, we unpack them using deterministic unpacking that we've just seen, and let it interact with all the other features in the ads ranking model. Similarly, for user history features, there's an extra dimension called sequence length. So we do the same, we consume the same, user history embeddings, quantize them using our side model, unpack them deterministically, and let them interact with other features with the extra caveat that we need to summarize this sequence length as well. Let's look at some offline results. In table 2, we first compare the SIDs produced through our DPCA method and k-means. We see that the normalized entropy is almost the same, but the cost of our SIDs or DPCA is much smaller than k-means. The reason for this is our features have much smaller length compared to k-means feature. Similarly, in table 3, we compare the n-grams SIDs produced through DPCA method but used as n-grams, whereas versus side, which is the deterministic unpacking. And we see that we improve the normalized entropy because there is no hash size collision in side, as well as we reduce the incremental cost because we only need one ID to be unpacked inside, whereas we need 3 IDs to produce this NE gain. And when we combine 6 individual features through our VQ fusion method and compares SID through DPCA and side, DPCA plus side, we see that we also improve normalized entropy with a fraction of the cost. And with that, we conclude our presentation. Thanks for listening.